Hey, what's going on? Hope you enjoy this nice little picture here. So let's start. Before we can start to understand why a sine wave in particular is a pure tone, we need to know how we actually hear sound at all. So let's look at this. First, the sound hits the eardrum, and then the eardrum vibrates with the sound and sends that physical wave through a few things until it gets to the cochlea, or inner ear. Inside the cochlea, there are roughly 18,000 hair cells, and each hair cell has many hairs on it, which are called stereocilia. Each stereocilia has a certain natural frequency it vibrates at, and when a sound hits that frequency, the stereocilia vibrates and sends an electrical signal to your brain, which then processes it as sound. For more on this, check the description. So, in short, a sine wave is pure because it will only activate one group of stereocilia. And by one group, I mean like one size of stereocilia, basically. And therefore, it only sends one signal to your brain. And the reason it does this is because the stereocilia naturally vibrate according to a sinusoidal function, a sine wave. And this is true for many things in nature. A pendulum's height as it moves back and forth, that's modeled by a sinusoidal function. A weight hanging on a spring that's bobbing up and down, its height is also modeled with a sinusoidal function. Lots and lots of things in nature are modeled with sine waves. And again, there's going to be additional reading in the description, so there you go. But why does a sine wave only trigger one set? Okay, like clearly, if it's only triggering one set, so a sine wave is a pure wave, mathematically speaking. But why can't it contain any like overtones or other information? Why can't it contain other waves? Because we know that something like a square wave, which actually seems a lot simpler to mathematically model, contains many sine waves in it, because it activates many different groups of stereocilia. So what makes a sine wave mathematically pure? And it turns out to be quite beautiful. The sine wave is perfectly curved. You can never multiply straight lines to get a sine wave. It's perfectly curved. First, we're going to talk about why it's perfectly curved, and then we're going to talk about why you can't multiply straight lines. So the way we know it's perfectly curved is through derivatives. The derivative of a function is the slope of that function at a given value, okay? So, oops, wrong thing. Here we go. This is a derivative. This is a little visualization of it. So the derivative of x squared, that's the graph there, for instance, is 2x, meaning that in the graph of x squared at x equals 3, the slope of the line is 6. Okay, so and at negative 3, the slope is negative 6, right? 2x. The derivative of 2x is 2, and that makes sense, right? Because the slope of the line of 2x is always going to be 2. Okay, no matter where you are. Most functions, if you find the derivative enough times, you'll end up with a flat value, a constant, just like this, okay? So we just did 2 derivatives and we got to a constant of 2, okay? But you cannot get to a straight line by deriving sine. There are actually several other types of functions which you cannot derive a straight line from, but those functions are not periodic, or they have an undefined amplitude, like tangent, for instance, which is a periodic function which you can never derive a straight line from, but its amplitude is undefined. Essentially, that means infinity. So, yeah. If we do some derivatives of sine, this is what happens. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine, and the derivative of negative cosine is sine. It goes in a loop. And the best part is, it never actually changes. Those 4 functions I just mentioned are all the same function, just shifted a little to the left or right, but they all have exactly the same shape. This means you never get anywhere when you derive sine. You never even start to approach a straight line, and you can never get there. If you take the derivative, on the other hand, of a triangle, saw, or square wave, with only 2 derivatives, you get to a straight horizontal line. I'll link another video in the description which goes through those if you don't believe me. Anyway, the point of all this is that the sine wave is perfectly curved. The slope is always changing, and the rate at which the slope is changing is always changing. and the rate at which the change in rate of slope changing is always changing, etc. The grammar gets really complicated, but essentially, I think you understand what I'm trying to say. It's perfectly curved. The slope is always changing, however many layers you go. Okay. Now, I also said that you can't multiply straight lines together to get sine, and the way I figure that is what your calculator does when it plugs in when you plug in a sine function. This is what it does. That's what I pulled up earlier on accident. So this is the function, okay? This is a little screen capture from the Wikipedia page, but this is what sine is. You can ignore this little sum notation if you don't understand that, but these are two different things, right? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, going on for infinity. So those so the exponents and factorials go up by 2 each time, and the minus and plus switch. So this function is a sum, but it is a sum with infinity terms, okay? And this sum notation, you see that infinity, that's what that means essentially. And to me at least, it seems kind of clear that a function that is, this complex, that is made using infinity terms is completely unique, and nothing you could try using normal functions could ever reach it. So, in summary, the sine wave sounds like a pure tone because it only activates one group of stereocilia in your ear and sends only one signal to your brain. It does this because stereocilia naturally vibrate according to a sine wave, and the reason a sine wave is pure to begin with, and why it doesn't contain any other waves which could activate other stereocilia, is because it is underivable, a perfectly curved function. Hope you enjoyed this. It was a little bit more mathy and physics and that kind of thing than I usually do, but I thought it was really interesting. And if you want to read further, I have several articles and whatnot linked in the description. So hope to see you next week. Thanks for watching.